Good afternoon, everybody. Welcome to the technical section 11 on the topic remote sensing. This section has 5 talks. The first talk will be given by Mr. João Paulo Navarro, and the title is 3D Poststack Seismic Data Compression with a Deep Autoencoder. Let's watch the video.
Hi, welcome to our presentation 3D Poststack Seismic Data Compression with a Deep Autoencoder. I'm João Paulo Navarro, Solutions Architect at NVIDIA Brazil and the presenter for this talk. Seismic surveys are images from the underground acquired from offshore and onshore regions and easy to support the oil and gas industry. The Poststack seismic data are 3D images computationally represented as scalar fields with 32-bit precision. With the increasing rate of sensors and acquisition technologies, the resolution of these surveys is getting significantly large. This way, compression technologies are absolutely useful to reduce storage and transmission requirements. The purpose of lossy compression is to minimize the trade-off between distortion and bit height, such that the loss of both is balanced. For this, in this work, we use a 2D autoencoder network to compress and reconstruct seismic datasets. In our model, we are using PSNR as a distortion function, while the bit height is estimated through a 3D convolutional network. The proposed multi-channel seismic data compression, or MSCS, was inspired by the work of Mentzer, initially designed for natural image compression. Here, an overview of the method. A seismic volume is provided as an input, and after an encoder forward pass, generates a latent representation and an importance map. This importance map generates a mask aiming to discretize the elements of the latent representation. Then, quantization is performed with the goal of discretizing the elements of this latent representation. This discretized volume is then passed through the decoder in order to reconstruct the input signal, and through a probability model, which calculates the joint distribution of the quantized latent representation, estimates the associated bit rate. In next slide, we provide more details. To train the network, we have a seismic volume or a set of 10 as input. Firstly, a normalization of the data is performed using the maximum and the minimum corresponding to each of them. Samples are extracted from all volumes to form a batch. We get the same amount of examples for each different survey to form this batch. And once the batch has been generated, it is passed to the encoder, and the outputs of the decoder and the probability models are used to calculate the loss. This process is repeated until the total number of iterations is reached. The models have been trained for 30 epochs. And regarding the quality of the reconstruction, we have noticed that it heavily depends on the training data. So, data with a balance between high and low frequencies are the most suitable to be used for training. At these balanced datasets, models generalize considerably well, but for very difficult surveys such as Poseidon with high frequencies, only with specialized training is it possible to achieve PSNR values above 40 decibels. In the second test, we compare the proposed method with JPEG 2000 and our previous approach to DSC. The tests were performed varying the number of slices served as input channels, D, ranging from 4 to 24, and the bitrate target from 0.05 bits per voxel to 1 bits per voxel. In this slide, we show a qualitative result compressing a bidimensional slice from the Penobscot testing survey, extracted in the inline direction. Even with an extreme compression rate of 320 times, the details are fairly preserved with a good PSNR of more than 42.
Okay, we're right on time. Is there any question? João Paulo Navarro is there. Do you hear me?
Yes, I can hear you.
Okay. So just one question you mentioned in your presentation that you run your training up to a number of epochs. Why didn't you try early stopping or something like that?
Yeah, so there's no particular reason for this. We just trying to test to perform the training on very different types of data sets, right? So there's no particular reason for this, but mainly because 30 epochs was a good number for most of the surveys that we tested.
Okay, there's here a question. Let me read it out loud. Hello, great presentation. I have a question. Did you contemplate the existence of missing data or acquisition errors?
This is a very great question. So at this point, we didn't perform any sort of correction on missing or wrong process data. We are just considering that the information is there, and during the normalization, we just get all the values between the range of 0 and 1, and then perform training. But this is a very point of a good point of interest, because in real life, most of the time we're not going to have the full field data sets, and this is in fact one thing that we need to do.
Okay. So one more question. I don't know if the experiments that you carried out allows you to draw any conclusion regarding the generalization of your methods. I mean, did you try to assess how well your methods performed on a data set other than the ones you used for training?
Yeah, and the table it's unfortunate that we didn't have too much time to path through the results. I really encourage you to get the full paper to actually get more details. We discuss with this a lot in the paper, and the result is that the final model, it's absolutely unfortunately at this point, it's absolutely dependent on the type of data that we choose for training, right? And there are some and the experiments still an open question to us for us. What is exactly the type and the set of training samples that we need to do to build a very good generalistic model, which we know is that depending on the training data set, your test set validation, your test metrics may be different and maybe better. So there is some type of surveys that generate better results, right? Even for unseen data sets. But what we are actually getting to the conclusion that we're probably going to need, and this is not do not hurt too much, because we have a lots of data to compress. When we're talking about the surveys, it may reach terabytes. So it's not an absurd to admit that we can have specific models, which is have a model being trained for a single data set. this is not a, this is one thing that we can actually can try, and we actually exploring this. So have a more generalistic model that can be good for most of the data sets, and then fine tune to specialize for a particular data set, since the benefits may be huge, because as I said, um, we can have surveys with terabytes and even petabytes, depending on the type of the data. Not exactly the post-stack, most the pre-stack, but this is one thing. So the short answer, yes, it's really dependent on the type of data that you use for training, and we didn't find yet the properly received to say this is the best generalistic model that we have for all the data sets, because the other problem is that the data sets are stacked and generated through a lots of there's a lots of steps to get these final images. So the data is different. It may visually be look similar, but they are different, mostly because the models that generate the signals, the images itself, are different from each other. So this is one question in within the community of deep learning applied to seismic data set, which is the generalization when you work with training in one type of surveys, processed by some sort of algorithms, and then you get to a total different regions, which has different geological structures, and also being captured and processed by different algorithms.
João Paulo, thank you very much. I think we have to move on, and let's then move to the next talk, which will be given by Eduardo Pinheiro, if I'm not mistaken. The title of his presentation is Generation of Turbidity Probability Scenarios Using Geophysical Methods.
Hello, everyone. My name is Eduardo Sarruf, and I'm one of the authors of Generation of Turbidite Probability Scenarios Using Geostatistical Methods, along with Angélica Pezzeri, Abelardo Barreto, and Sinésio Pesco. We're from the Mathematics Department at Pontifical Catholic University of Rio de Janeiro. So turbidites are deposits of turbidity currents, and they most importantly indicate potential oil reservoirs. Currently, this detection of turbidites occurs in an indirect manner, which involves indirect measurement by sonars in the context of offshore oil extraction. Therefore, there is a high uncertainty associated to the quantities found by these techniques. In this work, we aim to develop a geostatistical method to quantify the uncertainty associated with the raw data collected from sonars containing probabilities of existence of turbidite deposits. Thus, we try to generate multiple scenarios that are equally possible from this single data we obtained. In the scope of this work, we used a set of coordinates from the F3 field in the North Sea. This figure shows the disposition of the XY coordinates and the probabilities of turbidite deposits associated with them, ranging from 0 to 1. In our method, the first step was to produce a 100 by 100 matrix from the original set. For this, we grouped neighboring points to allow the smaller dimension, and we assigned p equals 0 to the points out of the field. Next, we defined 4 value ranges within the original interval from 0 to 1. And from each range, we selected all points with the 2 closest neighbors in the matrix in the same value range as itself. This bottom figure shows point A, which is selected because all of its neighbors are in the same range as itself, and point B, which is not selected. This way, we generated this set displayed in the top figure. Now, the set just shown is sampled, and we select a total of 30 points from its 4 subsets. These 30 points are shown in the figure to the right. The variogram for the matrix 100 is plotted, and the ideal model found was the Matern, with the values shown. Finally, we use the variogram, the 30 points selected previously, and the matrix to produce a sequential Gaussian simulation. This process involves the generation of space-time fields using a stochastic method. And we are going to consider each ensemble member generated as a possible scenario for the turbidite deposits in the original data. This figure shows the 30 ensembles which were generated by the sequential simulation process, and we can see that some of the desired characteristics are present. As we know, there was a concentration of high turbidite probability values at the left bottom corner, and it is reproduced in varying degrees by these 30 simulations. Similarly, the borders at the top respect a low value concentration, considering that in the original data there were unextracted points in these corners. This figure represents the map of differences between the simulated ensembles and the original data. And as we can see, there is a considerable proximity of the simulations to the raw data. For the validation methods, first, in the ROC curve shown in figure to the left, we expected an AUC value higher than 0.5 for the simulation to be viable, where 1 indicates a perfect score, and the area under the curve found was 0.787. In the CRPS process, 0 represents a simulation with no variance from the original set, and we found a CRPS of 0.1321. Therefore, we may conclude that the method developed can be used to further enhance the generation of turbidite concentration maps, and this property of the method can help oil companies on the estimation of high-value turbidite deposit areas, which can be prioritized before physical extraction of offshore sites. This is it. You can send any questions to the email in the screen. Thank you for your attention. Goodbye.
So back again. I'm waiting for questions. Hello. Is there any question? Eduardo, right?
Yeah, that's it.
Yeah, Eduardo, I have to say your field, so I'm not an expert in that field. This is completely new for me. But as I could understand from your presentation, you used statistical methods, right?
Yeah.
Purely statistical methods. I just wonder if there are some deep learning approaches for this kind of problem.
Well, actually, in the longer presentation, there was a future works section, and one of our ideas is to cluster these 30 simulations that we got and try to get the original set into one of those clusters to see which one could be the best. So yeah, there are some possible deep learning, artificial intelligence methods that could be used to further enhance the study.
And do you envisage some specific method for that? Generative networks or something like that?
We're still thinking about this. We still haven't gotten to this point, but it's one of the possibilities, yeah.
Okay, okay. And just one question. You work at the PUC Rio, right?
Yeah, that's right.
And Department of?
Mathematics.
Mathematics, okay, okay. So is there any question on that? I think this is a very specific field now of application, and maybe there are not many people acquainted with this problem. So I think I thank you, Eduardo. Our agenda is really very tight, and I think the time is over. So I have to go to the next speaker then. The next talk will be given by Enrique Andrade. And the title is Synthesis of Satellite-like Urban Images from Historical Maps Using Conditional GAN. So let's look at the video.
Hello, I am Henrique Andrade, Master's Candidate at the Universidade de Pernambuco. Together with Professor Bruno José Torres Fernandes, we discuss an approach for synthesizing satellite images out of historical cartographic documents. Historical maps are culturally rich and socially significant documents with which humans organize and communicate the spatial knowledge of the world. They serve as strategical documents that yield political representation to those communities there depicted. Historical maps are an irreplaceable primary source of geographical and political information from the past. The geographical documentation of some community in the past reassures the importance of its present existence. Likewise, the omission of communities in these documents erases them from history. Furthermore, maps serve as tools for controlling historical hegemony. Information presented in old maps might not be easily read by the ordinary observer. Additionally, historical spatial data is not as easily accessible as modern maps are. These documents are sparsely available on the internet or remotely found in museums and few public collections. As the reconstruction of maps depends on the available data of a desired region, literature discusses the application of a sort of computational methods. Nevertheless, the task of synthesizing a satellite-like image as a more up-to-date version of a map imposes a problem. A texture-based approach needs contextual representation of some dated urban architecture layouts, including its long-modified natural surroundings. In image-to-image translation, segmentation maps are often used as context-driven inputs. We consider context to be the localization of textures to reproduce visuals from the time period of the analyzed map. Context brings semantics to our architecture, which yields a more convincing synthesized image for the observer. In other words, gathering our system's inputs requires supporting data that justifies the use of such inputs. Different inputs may be more appropriate for a desired representation. Textures depicting urban settings will likely yield a more realistic urban-like output, as natural landscape textures will probably represent nature better. As each divergent input sets may be better at representing some specific classes, our solution proposes a merge of different training results. We first generate different label maps, we then apply peaks to each of the results. And finally, we merge the translated label maps into one final image. To merge, we specify which label each translated image was trained to focus. The result is a composition of regions of interest from the inputs. We executed two experiments with different sets of inputs. The first set contains images of current-day Recife, hence a more predominantly city-style imagery. Thus, the urban setting is our label of interest. The second set covers more rural areas and natural landscapes from areas around Recife. We compare our results with the output of the state-of-art Pix2Pix. Comparing those results with the contextualized outputs from our first experiment, one can observe textures from a particularly modern urban setting. Other visual elements resemble settings yet to exist and do not reflect the mapping analysis period of time. In parallel, the second experiment results display a focus on synthesized natural aspects. As the second set of label maps does not contain dense urban settings, buildings were poorly represented when compared with the results from the first experiment. A combination of the results of both experiments shows a closer representation to the description of the object in analysis. Merging results, considering the pixels labeled as urban settings from the first experiment, and applying them to the second experiment results, yields a trustworthy output. We would like to express our gratitude to the agencies that allowed the development of this work, and also to your attention. Thank you.
Hi, Enrique. Thank you very much for the presentation. And we have time for questions. Well, while the audience types the questions, I want to make a question. Hello.
Oh,
So
hi,
I saw in some of the results you showed that you have a kind of this patchy effect. So you see that you have you made a kind of mosaic of the results you obtained in different patches, and
that is true.
we can see well, the borders of those tiles, these patches.
Yes.
Is there any way to avoid that?
Well, this is one of the limitations of the current of the installation of Pix2Pix that we used for this work. The patches have 256 by 256 pixels. And this is actually one of the future works that we're developing right now.
Okay. I have here another question. I cannot identify the person who sent the question anyway. This is Chihi Roku, I don't know. The question is the following. Did you use any metric to evaluate the performance of the method besides the visual analysis? GANs are well known for generating hallucinations. Did you observe this effect in your experiments? Thanks.
These are interesting questions. So for the first one, we didn't use any metric for quantitative results. Um, it is basically the generation of synthetic images. So for a matter of comparison, because we're using segmentation like label maps to create like a local language for both representations, the ancient map and the satellite image. So we segment both of them so they can understand each other. But when we use the same technique without doing this translation in between the segmentation maps, we have some kind of hallucination, and it is in the work. You can check it out after this presentation. So answering the second questions, yes, it is very likely that we get hallucinations, but when we use the label maps to identify what pixel belongs to what kind of category, then we avoid going to this kind of generation. So we could escape because of this method of creating segmentation maps before applying pixels.
So thank you, Enrique. I think, well, we would have time for one more question, for one more short question. Well, it doesn't seem to be the case. So I want to congratulate you, Enrique, for your work. It's quite interesting. I can understand that you were not able to, you don't have a ground truth, of course, because you don't have satellite images from that time, right?
Yes,
Yeah, of
that's true.
course. But this is an unavoidable hindrance. So thank you very much again, and congratulations for your work. Let's move to the next speaker. The next speaker is Laura Helena Cuela Rosa, and her topic is entitled Learning Geometric Features for Improving the Aromatic Detection of Citrus Plantation Rows in UAV Images. Let's watch the video.
Hello, my name is Laura Helena. I'm a PhD student at Pontifícia Universidade Católica do Rio de Janeiro and also an intern at IBM Research Brazil. Today, I'm presenting a work developed at the research lab at IBM, entitled Learning Geometric Features for Improving the Aromatic Detection of Citrus Plantation Roads in UAV Images. Accurately locating trees is a critical step in the aromatic monitoring of orchards and farms. Alongside, UAVs allow on-demand imaging of orchards at unprecedented level of detail. However, citrus trees can be planted in curved roads that form intricate geometric patterns, raising the need for robust computer vision approaches that can help to detect plantation roads in extensive areas. In that context, deep learning ranks among of the state-of-the-art approaches for segmenting image with geometrical patterns. A well-known approach for semantic segmentation is fully convolutional network. Such segmentation networks often achieve high accuracy, despite having low generalization capacity and not rarely requiring fine-tuning to have good performance on new data. This approach relies on the fact that the learned features are similar among different images. Such an assumption would likely be problematic in some remote sensing applications, since geometric patterns and vegetation characteristics can vary substantially between training and testing images. If we test the method in a new image, for example from a different region, the prediction will likely to present a poor performance. In this work, we present a proposal for learning complex geometric patterns and robustly detecting citrus plantation roads in UAV RGB image. The goals are twofold: embedding more knowledge to these models, such as shape and geometrical features, and at the same time, decouple detection and geometry learning. The proposed methodology consists of a two-stage framework based on fully convolutional encoder-decoder networks. First, we train an encoder-decoder network to detect planting roads that, as discussed previously, will probably fail for images that differ from those observed in the training set. To overcome this problem, we use a second encoder-decoder network to correct geometric inconsistencies in the prediction produced by the detection network. The correction network will enable learning intricate geometric patterns of orchards that simultaneously respect some simplest aspects, such as the regular space between roads. In addition, the network will conform segmentation masks with faulty geometry to the distribution of commonly observed geometries in the training set. Alongside, segmentation geometries belonging to this distribution will remain unaffected. The dataset is composed by 45 commercial orange plantations located in Santa Cruz do Rio Pardo, São Paulo, Brazil. We randomly divided the 45 orchards into training, validation, and testing sets. We also simulated degradation scenarios by applying increasing levels of Gaussian blur to the RGB image in the test sets, resulting in three different corruption scenarios: low, average, and high. We compare our correction method with a post-processing approach based on U-transformation. We assess the accuracy of the method using three scores: completeness, correctness, and quality. Table 2 shows the mean and standard deviation of the accuracy scores for the orchards used for testing. As observed, the detection network predicted the plantation rows in original test images accurately, and neither the hue transformation nor the correction method introduced a significant change in the segmentation results. Regarding the completeness, the correction network was consistently the most accurate solution for all levels of degradation tested. Regarding the correctness, the detection network presented a firm agreement to the ground truth reference, scoring above 99% for all degradation levels. Conversely, the correction network ranging from 98.2% to 98.9%, suggesting a small level of over-segmentation. Finally, Q-values show that the proposed correction network could significantly improve the detection of the plantation roads. The correction network restored more of the discontinuities and spurious segmentation patterns as indicated by the red ellipses turned into green in the top row. However, we still observe an undesired over-segmented line for the three methods, and artifact introduced by the correction network. We pretend to address these issues in future research. As conclusion, this work proposed an alternative to improve the aromatic segmentation of plantation rows in RGB image of citrus orchards. The primary contribution of our proposal is an encoder-decoder network that corrects segmentation errors. Our experiments show that the correction network could restore information and provide accurate segmentation results. An extensive evaluation of our methods could help us generalize conclusions and points to further research.
Hi, Laura.
Hi.
Can
Hello.
you hear me?
Yes.
Hello. I have a question. The sound on my computer was really bad. How was it in your computer, Laura?
A little low, but if I change the sound level, I can hear. I could hear the presentation without any problem.
Yeah. Okay. So for me, it was really hard to follow your presentation. But anyway, maybe some other people in the audience had the same problem I had, and maybe they did not follow everything that you presented. So I just want to make a question. I made a lot of questions regarding this work before, but let me do it again. Would you tell us why is it so important to detect this plantation rows in UAV images? What are the benefits of it? What are you going to do with this information?
Well,
I don't know if it is clear.
yes. The question? Yes, it's clear. One advantage could be, for
Laura,
example, for yes.
Yep. Maybe the problem is on my side. I can hear you with some interruptions, but go on.
Well, one advantage could be for those auto robotics that pass through the plantation roads for counting or other monitoring tasks. Other advantage could be for geolocating the plantation roads or further process the information within the road lines, detect, for example, gaps or full-grown trees, and monitoring the orchards. That could be another application. Other common application is to detect weeds between roads. Then the first steps is commonly the road detection for further detect the weeds and take an action before the problem goes bigger.
Hello, Laura.
Yes.
Can you hear me?
Yes.
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 Okay. Any question from the audience? Yeah, Laura, I think well, there might have been some problems with the recording. I don't know, but in any case, our time is over. I thank you very much for your talk, for your video.
Thank you very much.
And we will move to the next speaker right now. Thank you, Laura. So our next talk will be given by João Gabriel Vignoli, I think that's the way you pronunciate his name. And his presentation is entitled CNN-based change detection algorithm for wavelength resolution SAR images.
Hi, I'm going to present you the CNN-based change detection algorithm for wavelength resolution SAR images. My name is João Vignoli, and we are with the Federal University of Santa Catarina, the Aeronautics Institute of Technology, and the Black Institute of Technology. What is the synthetic aperture radar? It is an airborne or orbital pulsing radar. It measures the intensities and phases of the reflected pulses, like any other radar would do. But it has a virtual aperture, which provides a high azimuth resolution and is independent of weather conditions, which is a great advantage over optical images. And change detection, what it is? It is used as an application of SAR images to detect changes between distinct instants of time in the same scene. It is used for defense applications, deforestation monitoring, urban planning, and ocean monitoring, and it is usually performed by Bayesian methods or by other classic signal processing algorithms. And it requires two SAR images, the image to be monitored and the image of reference. Wavelength resolution SAR system is a system of radars that operate in low frequencies in the VHF bands and generate speckle-absent illuminations with, in other words, it is free from multiplicative noise, and the resolution of the illuminations are in the order of the wavelength of the transmitted pulses. For this reason, it achieves maximum resolution, and small scatters are ignored, such as leaves and little rocks and other objects that are in the scene that are small, and produce illuminations that are stable in time, which favors the change detection. And the Corabas-2 dataset consists of 24 incoherent wavelength resolution SAR images, with targets concealed by foliage. These images, each one contain 25 military vehicles concealed by dense vegetation and are from the northern Sweden and were made available in a challenging problem and have been vastly used to develop change detection algorithms with more usual techniques. Here are some examples of the SAR images from the Corabas-2 dataset. Here are the dots that represent the targets concealed under the foliage. The foliage is here, and the proposed algorithm comes in place. Here are the monitoring image and the reference image. We subtract one from other, and we have the difference image, which represents the difference between the two images. It is then analyzed by the segmentation CNN, which will spit out a probability map representing the probability of each pixel being part of a change or not. Then it is threshold by threshold omega-1 pixel-wise to determine which pixels are the most likely to be parts of changes. And the DB scan localizes these clusters of pixels and determines them, the central coordinates of these clusters, and send to the classification CNN, which will analyze the patches around these centers of possible changes to determine whether these possible changes are really changes or are false alarms. The details of the algorithm, the semantic segmentation, the different image comes, and the CNN generates a probability map, which is then binarized. Here are the parameters, and the DB can localize these possible changes in the binary mask and send these patches around the points that it found, the points of clusters, to the final CNN, which will classify individually these clusters, these patches, and determine whether they contain or not a change. And the green circles are true positives, the yellow squares are false negatives, and here in red is a false alarm. Here are the parameters of the model and obtain the results. The matrix of choice is the probability of detection, which is the ratio between the number of changes detected and the total number of changes, which is the recall of the system. And the false alarm rate, which is the ratio between the number of false alarms per image divided by the area under surveillance, which is, in this case, for every image is 6 kilometers squared. And the performance is presented in terms of a ROC curve, letting omega-1 equals to 0.68, which is the threshold of the segmentation CNN. The final evaluations are performed. We can see that our algorithm has surpassed in performance other state-of-the-art techniques, here in blue. And here in purple is the curve of our algorithm without the classification network, which has already presented a good performance. But with the classification, then with this classification CNN, we can increase performance such that we can plot these points in the blue plot. And a possible limitation is that the classification network has been trained with a limited number of examples of changes. In the end, if we want to detect changes whose morphological attributes are much different from those changes present in the Karabas-Chu dataset, we naturally would have to retrain the models with more representative examples. Thank you for your time.
Oh, João
Hi.
Gabriel.
Yes.
Hi, are you there? Yeah. Well, change detection is a hot topic in the remote sensing community, indeed. And well, I saw in one of your slides. Of course, you cannot show it again, but you use as input the difference image, right?
Yes, that's right.
Well, one let's say conventional approach, if I can say so, in deep learning for change detection is what we call early fusion, where you concatenate the images along the third dimension instead of computing the difference. And a second approach is the so-called Siamese networks. Why didn't you try those methods, at least to use them as a kind of baseline?
Well, we are planning on doing that in future works, but we also wanted to try a more simple algorithm to approach this problem in a way that other works haven't already tried to bring this solution. So the Siamese networks that you said are in fact a possible future work subject.
Okay, so I saw here a question came in, which from Chihiro Hokue. I don't know who's the author of this question, but well, the question is exactly the same. Why use subtraction and not, for example, the commonly used image stacking for change detection? Thanks. So you said that you had to work with few training samples.
Yes.
Don't you believe that you incurred in a kind of overfitting?
That's a worry. We have thought about this, but we try to perform at least a cross validation with the k-fold cross validation.
You did it.
Yes.
Mm-hmm. And how
it is
did
detailed? Sorry, can you repeat?
You separated your data in chunks, right?
Yes. We gathered these 24 images and separated in 6 folds, 6 sets of image. In each set, there was a training set and a test set. So in the end, having the 6 divisions, all images have been used to both training and testing for different models. But to develop the model, the algorithm, we have previously selected 20 images from the 24, so that the 4 images that were selected to develop the model were separated for the final phase, for the test phase, in order to really evaluate whether we have not overfit the model, the architecture or the parameters to those 20 images. But it is a problem very, very hard to solve in the SAR field, because to gather these images to capture, you need an airplane, you need a very expensive materials.
Yeah.
So unfortunately, not like it is not like in optical image classification segmentation, where we have thousands or millions of images to train. So we had to work with this method with simpler networks, with fewer parameters that you would see in optical images classification, etc. And But a thing that is in our side is that these images are very simple in geometric features. Is not like a photographic image where you see objects in perfect form. These are much more like an X-ray of this forest, in not very easy to see the form of the objects. It is used only to detect if something is there, not to detect their appearance, not detect the form of the object. So the training could be, for this reason, we believe we have not overfit the model so much that as we would have overfitted, we have used optical images from satellites, etc.
Okay, so thank you very much. I would have some other questions, but I think our time is over. We are 2 minutes beyond the time. I have to close this technical section right now. And I want to thank again all the speakers and the audience for the questions. And I wish you all a very useful and instructive rest of conference. Thank you very much.